keep yourself here and live long enough to see your result. That's the first thing we should learn. Okay, so any comments and questions? Yeah. Great overview. Great overview. I also want to make comment. This Jia mentions this dynamic conjecture. That I already said that he offered a course when he did that further, and I took that box spline course, end of a course. This topic course, not like every other professor, he signed a paper to every student to read it. Then when they gave it to me, that this is the dynamic listen paper, and at the end of the paper, there is a conjecture. You are just starting your PhD, you can solve it in your PhD. Get your green. That's what they told me. So that's why I started solving. So you owe me something. Yeah, all the community. So I started by bringing about Fox back. Yeah. Okay, thank you again. We have a tea break and come back again.
That was very nice.
Oh, thank you.
Lovely reading.
Okay, and before everything, I think tonight after workshop, we can Ines asked me if all the people want to go back to hotel first, and they can arrange a bar. So if we say only 2 or 3, they don't want to arrange a bar. So everybody want to go back to hotel or something first. Then we okay. So I can ask them arrange a bar.
Did you give Zoe a copy of your presentation? Is it on his?
Yes. No, I don't know. For sure in this machine.
Okay, so I need to give him my presentation.
Yeah.
Very nice, thank you. The lemma of De Boer, Jia, and Pincus is a lemma. It's a lemma.
It's a lemma.
It's not difficult.
But didn't we prove it?
Yeah, but it's not difficult.
Not difficult.
Well, for me, these total positivity things for me were it's obvious. It's one of the things that I had a feel for. No, we proved it.
It's easy to prove at least.
You have to remember this paper also partly we wrote by email. It was not email.
That time we didn't have email. Regular mail.
We would write and you would write, and sometimes the same proof would go both ways.
Yeah. No email.
No.
No email.
Yeah, but these are from the counties I couldn't find from my list. Because we have the one name from my land.
Just for every projection. And then the only thing what
So this one explains the Tensor Products, and meditation. Oh yeah, this is the only one that can explain properly. Some of these blog. So you're going to fly back from Mecca. Also, you still have This has first class.
When how hours is that?
These are all at the first class.
You end up taking a taxi, then this will waste the money.
This is Sunday night. Yeah, no, this is
I have a worst case scenario. I'm hoping the second class was. That's my fear. But at least we know that they are trains.
yes.
It's just that
But you know, this is this Jetstar. I don't know how much I can trust Jetstar that it leaves here all the time and gets there on. Jetstar is based in Singapore. But it's a low cost.
It's a low cost. It's a very I took it once in Paris.
Yeah, because it's like, why go from Hong Kong and spend 8 hours to get them? Say, you know, that's incorrect. Come on.
Some of the low-cost airlines flying out of Singapore, Scoot for sure,
Scoot, yes.
possibly Jetstar, have brand new airplanes.
Really?
Yeah, I mean, they're these lovely fleets. We flew from Athens to Singapore on Scoot. Brand new 787, $350 one way.
Scoot is owned by Singapore Airlines.
Yeah.
Yes.
The plane was half full. It was a fantastic experience.
Great.
I don't know how.
What's the name of this company?
Scoot.
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 Yes.
Yeah. The
There's
logo
a-
is Scoot to Singapore.
There's
So-
airlines called Wizz. Do you know Wizz? Yeah. There's a, I think it's Hungarian based or something like that. There's all, nowadays there's,
Yeah,
I
I
fly
know.
to Israel, like,
Yeah,
these
that's
airlines,
what they make.
I don't know if these
Never
are.
give you a ticket.
Scoot is a spin-off of Singapore. It's their experiment in the low-cost market. I mean, you have to pay for everything. You want to check a bag, it's a little bit extra. You want to
Southwest.
well, Southwest operates the largest
Oh,
737 fleet in the world.
Just to the west of the southwest of the hotel.
The south end is Lake Washington.
On the road.
All summer
I
long.
used to live, yeah.
There were 8 brand new Southwest 737 Max just lined up there.
Yes, and so to get here.
A few miles south of my house, I drive past.
I used to walk by that restaurant.
You know, this is $500 million worth of inventory that is just sitting here waiting for the FAA to certify these planes so that they can be delivered.
So I passed that by.
No, but
It's
at the
amazing
point
the
when
differences in
FAA
prices.
certification arrives, one wants to have the production system running full throttle. And so it means manufacturing in advance planes that you know you can't deliver until certification.
Oh, none of them. Yeah, but that's a cheat all over the world. We even have that in Israel. So the water Japanese. The star is above Japanese.
Who else will do it?
So we want.
There is a
Sunday,
lovely
we
mathematical,
They become, yes.
really, it really is a
Kansas,
mathematical
walk around.
initiative
I said,
at the Boeing
she has no
Company.
sense of direction.
Called certification by
I'm going to go to the
And
courts.
the thrust of the whole thing is
Just in the-
every time you
There's a series of,
present the FAA
on the
the results
south
of
side.
some
Just
computer
past the
simulation
road,
you
you
would
go
run
over rise and go
in
to-
lieu of an expensive constructive test,
And
flight
that's
test,
where we used to.
static test or something.
That's where we used to.
And so it's this big,
But I remember on the other side.
the discussions between Boeing and the FAA don't
All in
take
villages.
place at
Expensive.
a
Just on
sufficiently
the other
high
side,
technical
just
level
west of Buena Vista,
to
there's a whole bunch
permit
of high
the
rises.
right
and
things to
underneath
get
there,
done.
there was
But-
a.
To accept
So I thought maybe so
That's a big part of the problem. They're not.
Okay.
Newton or something.
These are, many of the people who work with the FAA are underpaid civil servants. And, I mean, it's really like,
There's
the
no.
military does a much better job. Considerably more expertise than civil salaries. This is my problem.
But it's listed.
Oh, okay, I'll run it over there.
But that's most famous that there used to be. I remember, why, there's this restaurant that operates like, that there's a big mall before you get to San Jose, near the harbor. Yeah, you go up and there's a restaurant.
I'm just not enough.
And many different, what's it called? Vivo City?
So, only has sand.
That would be more.
He has no shoes. Only has sand.
How do we not display the lot? How can we not display? I don't like to display that in lot. Is there a way to not display? Okay. I need to download mine from email.
Okay.
Makes that easy.
This one?
Should be fine, right?
Should be fine.
Yeah.
Good, I didn't take that picture.
All right. Thank you.
She picked
Yeah, I'm already in there. I would like to not display this for the world.
Okay, sure. Yeah, change the.
That's it. Oh, and can the talk be given from this?
From
Is it faster? Yes, I can do the on the safe side and do a backup, right?
yeah, it's faster. It should be faster.
Well, this has the advantage, which I don't have. This has the advantage if you actually present, you can actually see your talk with your own display your own.
I think it's the downloads.
Oh, actually, I just saw it. Oh, let's show this one. Escape.
So this is the next pointer is it? So forward back middle. Then we will.
Maybe the next one speaker.
Yeah. All right. Okay.
And I want to show you
Tell me that I have to work hard now, so okay. So I have to chair the rest of the talk. Yeah. So we are going to talk about applications. Yes.
One in particular. This one.
So is spline function used in the Boeing airplane?
Oh yes.
Oh, the 737, everything. Everything. I always believe that spline function, because I know that you work in Boeing, so I always suspected that spline function is used in a plane.
In a big way.
In a big way.
Yes.
Probably 1 minute.
Boring? Is that
No,
what you
Boeing.
said?
I said Boeing.
But it's still pretty tough. Thanks for starting. You go into a restaurant, the prices are like this. You go to a food court. $50, $3.
Is this your first time to Singapore?
It is.
Oh,
I'm delighted that you come.
I see.
Hot air hasn't even started.
Okay, welcome back. And just in case you are wondering how come I'm introducing the speakers, because Joey has graciously passed me the chair job for the rest of the workshop. So I will chair all the other sessions until the end of the workshop. Unless Ji Hui would like to chair the rest, some of the talks. No. Okay, so for the this coming talk, we have Thomas Grandine from Boeing to tell us about how spline function is used in applications. You know, whenever I take the planes of Singapore Airlines, I always wonder, is spline function, are they being used? And finally, I get to hear some insight from Thomas Grandine. So let's welcome the speaker.
Thank you. I was so honored by your invitation, and I was delighted. The whole way this has been handled from start to finish has been magnificent. So thank you very much.
I thought I would follow yesterday's precedent with a couple of photographs of my own. The lighting on this picture isn't very good. This was in December of 1985, 22 years ago, when I finished my PhD. And then a few moments after that photograph, this one was taken. That's my grandmother, and this is Carl meeting my grandmother for the very first time. What you may not have known is that of her 4 grandsons, 2 of them graduated from Wisconsin that day. My cousin Bob earned a bachelor's degree in agronomy, so she had good reason to be there. What I have always liked about this particular photograph is the look of pleasure at being introduced to my grandmother is absolutely sincere. And so I have always treasured this particular picture. Then here's another photograph. This one is on your website. Several of us in the room are in this photo. This was for the 100th anniversary of the granting of the first PhD in the Department of Mathematics. No. Because the university wasn't even 150 years old at that point. This was for the 100th anniversary of the granting of the first PhD in mathematics.
Who's the guy, the corner, the left-hand corner, second row?
That's Kang Zhao.
Oh, right. Now I remember.
And you see Scott right here. And the interesting thing, I did not know Tom Hogan when this photograph was taken. And he and I were both startled when we looked at this photograph 4 or 5 years later to discover that we were both in it. Because Tom Hogan and I have been colleagues at Boeing for the last 16 years. And so, but we did not know that we appeared in this photograph together before we had ever met. But there we are.
So what is the years that you mentioned? 1990?
1997.
1997.
I don't know where you were around. I don't know where you were.
I was out of town or something.
All right. Onward.
So your Peters was, this was a meeting or what?
This was a...
This is your memorial union.
Yeah, that's the armory. That's the old armory building.
Right. So how your Peters appears in the... He was not in Madison for a long time. Photoshop.
It was a little conference, and yeah, okay. Okay, so I'm actually only going to talk about one application of splines at Boeing, although the application has several applications of its own, and in particular, what I really am going to focus on is imagine that you have a tensor product spline. Actually, let's make this M separate tensor product spline mappings from Rm to R. And imagine I have these M functions. I want to know, in this M by M system of nonlinear equations, where are all of the real roots defined over some box in Rm. That really is the application of interest today. And I did a quick back of the envelope calculation. I think we solve, the ones that I can account for anyway at the company, we solve these M by M tensor product spline systems of equations about 200 million times every day. Some of them are only 2 by 2 systems, and you have some 3 by 3 systems. Occasionally, you'll get a great big one, like a 9 by 9 system, which I'll show the application of the 9 by 9 system as it comes up later on. But some of the ways this arises is, imagine I've got a pair of tensor product surface mappings, each of them, say, from R2 to R3. And I want to find the curve that those surfaces have in common. I can write the x, y, and z coordinates of those surface maps equal to each other, and I get I get 3 nonlinear equations in the 4 variables. 2 of the parameters for the first surface, 2 parameters for the second surface, 4 unknowns altogether, the 3 equations being the x, y, z coordinates. It's underdetermined, and so what you expect is a 1-parameter family of solutions in general. But to get started on that, you actually have to find where those intersection curves start and end. And so to do that, you have to reduce the problem to 3x3 systems, which you get by taking an edge of one of the surfaces and intersecting it with the other surface. So you'll take all 4 edges of the first surface and intersect it with the second, and then all 4 edges of the second and intersect it with the first. And then you have to solve some 4x4 nonlinear systems to identify the closed loop intersection curves that might not intersect any of the boundaries, and then some additional ones that you have to solve to resolve the topology of all of that, all in an attempt to reduce it to 2-point boundary value problems that you solve to get the intersection curves. That's a wonderful topic all on its own, but I want to focus now on the sub-problem of solving these square systems just to get that.
Thomas, may I ask you a question? So what you are doing every day? You are developing new aircraft, or what is the purpose of this?
We have, there are any number, I mean, I don't have a good estimate for this, but I bet we run 5,000 CFD analyses every day.
What is the purpose for that? It's for new aircraft?
It's for new aircraft. It's to run test cases for old aircraft. Sometimes it's in support of sales campaigns for airlines. Airlines want to be sure that that the plane can actually fly some special thing that they do with it. Oh boy, we need to be able to take off with one engine from 8,500 feet through a tight canyon with mountains on the left or whatever. And so show us the simulation results that will demonstrate that your plane, should we decide to buy it, can fly our mission.
Are you trying to find also the limitations? So what are the limitations of, say a quick rise or like this, in terms of the stability?
Certainly in a design setting, that's the case. No. I mean, the limitations are well understood before a customer gets even the one airplane. And in fact, those things will be understood pretty much before the test pilot even gets to sit in the airplane and fly. We'll have a pretty good understanding of.
With high speed, there's a lot of cushion. I mean, is there an intent to find the real?
Yes, because the way each succeeding generation of airplanes becomes better than the previous generation of airplanes. Part of that is by mining the margin that you left in the previous generation of designs. So the sophistication of the analysis capability gets better and better all the time. And that was one of the reasons I was so particularly interested in your presentation yesterday, because what you're doing resonates. I mean, we have these parametric families of airplanes, and you want to be able to understand what is drag as a function of the design parameters. And yeah, it's the problem is very real. And so when you were talking about these things that to me were new ideas, the application of them is very real to me. Structured meshing, you can't count on the parameterization of these surfaces being nice and polite and friendly. And so you have to do a lot of slicing and dicing and projecting to make sure you get nice computational meshes. And this is the source of probably the bulk of these 250 million spline systems every day. And then you've got ray casting, curved surface intersection. Again, sometimes that's for very fancy display purposes. Sometimes that's for mesh generation. Sometimes it's for mesh refinement.
What's ray casting?
You are, from the computer graphics point of view, it is to locate a point at your eyeball and cast a ray toward a screen that goes through a certain pixel on the screen, and then understand where it intersects the object in view, and then understand the relationship of the surface normal to where that ray intersects for getting the lighting model right and all the rest of that. And the highest quality computer graphics images are generated by casting tens or hundreds of thousands of rays. But the thing that characterizes all of these problems is A, they're nonlinear, B, you have to reliably calculate the answers to all of these. So you have this inherent conflict between the nonlinearity of what you're trying to do and the fact that you're going to try to do this 200 million times successively and get the right answer every single time. And that gets to be the real, one of the real challenges in all of this. So because you're doing this 200 million times, speed is important. You want to be able to do this quickly. But at the same time, because you never want to get the wrong answer, even more important than the speed of doing this is to find all of the solutions of this system reliably. Okay. So just to make the point here again about reliability, typically on average you have to solve about 20 of these systems to perform one surface intersection. And because you have to get the right answer for all 20 of them in order to get the surface intersection, you've got this P to the N phenomenon going on right here. If your probability of solving one of these nonlinear systems correctly is 99%, well, now you've only got an 82% reliable surface intersector. And even if you can bump that up by another order of magnitude, the surface intersector is still going to fail 2% of the time. And P to the 200 million for P essentially not 1 is a very small number. And so reliability is key. This is the 737 production line. We're currently building 47 737s every month, 3 every 2 days. I could go back and see what I can do about getting discounts, but the list price is about $125 million for a brand new 737. Drop in the bucket. If we all went in together, maybe we could share one.
That's the Dreamliner, yes, right? Dreamliner, 737.
787 is the Dreamliner. Okay, so in terms of solving tensor product spline systems of equations, there really are 3 references here. I guess I put these in alphabetical order, but chronological order is maybe the more significant one. The real first paper here is the one by Sherbrooke and Patrikolakis in 1993 that describes the projected polyhedron method, which I'm going to go through in a few moments. And then about 10 years after that, Bernard Morin and his students at INRIA published a lovely paper exploring some of the algebraic structure of these systems and presented some very useful and practical preconditioners that sped up the solution here. We have these last two things are currently in production at Boeing and solving these 200 million systems a day. The paper on top, the one by Ido Hanil, is a more recent paper, and in this paper, in one of the early paragraphs in the paper, he describes an approach for solving nonlinear systems of equations, which 2 paragraphs later he discards as impractical. Says, you would never do this, so let me shift my attention to something else for the rest of the paper. And I was so intrigued by this idea that he threw away that I decided to take a closer look at it. And I think this idea that Ido discards in his own paper is in fact a lovely idea that is far more general than tensor product splines and worthy of considerably more investigation. Alan, do you know Ido? He earned a PhD at Technion.
Undoubtedly in computer science.
Yeah, he was Gershon Elber's student. And his thesis was on this topic, and this is a follow-on paper. I think he must have earned his PhD, I want to say 2010, 2011, something like that. A couple other things I should say about these papers. They all exclusively focus on polynomial systems of equations, and yet you look at the algorithms that are published, and with the exception of the preconditioner in the Bernard Morin paper, there's nothing polynomial about the algorithm at all. It will work for splines. Everything involves the structure of splines and the arithmetic of splines and B-spline coefficients, and it generalizes without any thought at all. The other thing is that these are exclusively numerical methods rather than algebraic methods. Okay, and then necessarily, of course, they focus on robustness. All right, so let's start with the projected polyhedron method of Sherbrooke and Patrikolakis. This has, in fact, been the workhorse method in our own software for the past 25 years, and it performs pretty well. And the basic idea here is that I've got a spline function represented as a linear combination of splines, of B-splines, and I want to figure out the value of x that vanishes at. So let's take a look at what this algorithm looks like in one variable. The basic idea is that I replace the B-spline coefficients of the function f with the control points for the graph of f. So I now use as my coefficients of B-splines these 2 component vectors, xi, alpha I. The xi are the knot averages. They'll be the B-spline coefficients for the function of x, which is x itself. And what I can do, now having those 2 component vectors as spline coefficients, I can plot all of those. And what I know, because I listened to Ja's talk an hour ago, is that the graph of the function f must lie inside the convex hull of these control points. And so in particular, I can look at the convex hull of those control points, and if I'm looking for zeros of the function f, in some interval like this, I can take the intersection of that convex hull with the x-axis, and that's going to give me some reduced interval over which any zeros of the original f must necessarily lie in this reduced interval. And what I can then do is then trim the spline to that reduced interval and get a smaller box and repeat as necessary. This isn't the end of the story. This is just in one variable. the way Sherbrooke and Patrikolakis presented this is for tensor products. And the basic idea here, I now have a function of two variables, and I can think of, with the tensor product structure, the coefficients of the spline function of x as themselves being spline functions of the variable y, complete with their own b-spline series. So in particular, if I now want to think of this tensor product spline function of two variables as just a function of the single variable x, what I know, again taking advantage of the properties of b-splines, is that my coefficients, my b-spline coefficients of the function, the spline function of x, have to lie between the smallest of those alpha ij and the largest, that there's a bound. So what I can do, again, I look over the alpha ij and take the minimum over all j for each I, and the maximum for each of these not average locations in x. I now will get a pair of values that I know that the spline coefficients of y have to take on at each of those locations. And I know that thought of as a function of x, any place where the function f vanishes as a function of x has to lie in the intersection of the x-axis with the convex hull of that guy. And this can be generalized to an arbitrary number of independent variables, and everything still works. Yes, sir?
This is a dissection, right? So it's a auto one convergence.
Yeah, this is...
So you don't switch to a new, and you are closing on?
As a practical matter, you have to. But what you really can do is you can squeeze these intervals down, and in Bernard's paper, and also one that I didn't cite of Gershon Elber's, it is possible to, there's a test that you can perform to say, I know that there is a single root in here and no more. And you can count number of spline changes and coefficients, and there's lots that you can do to gain confidence that way. But yes, the method, as you might expect, is very slowly converging. And I should say that if you're trying to find functions of a single variable, zeros of a single spline function of one variable, you would never employ this method. The interval Newton method, right from the get-go, is the best method out there. And you get quadratic convergence even with very large initial guess intervals. Okay, so now let's put the whole projected polyhedron algorithm together. Suppose that I want to solve two equations and two unknowns, both of them tensor product spline equations. Well, what I can do is consider first x, or f, and I have this convex hull by projecting everything onto the x-axis and taking the intersection. And then I may get a different convex hull for g. I want these two functions to vanish simultaneously, so I can take the intersection of all of this, the intersection of all the convex hulls with the x-axis, and when I do that, I get this greatly reduced interval. Any place where both functions vanish simultaneously has to be there. All right, and so as a high-level algorithm, here's really the whole thing. You start with the first independent variable. You project each of the graphs of the control points of the graphs of each of the functions onto the plane, generate the convex hull, trim the splines to the smaller interval of definition, and then here's the key step, which is if you haven't sufficiently reduced the size of that interval, And I have found in practice 30% works pretty well. That is, if I haven't pruned away at least 30% of the interval, then say, all right, we're going to split this into two subproblems. I'm going to, the next time I deal with this, I'm going to take the left half of the reduced interval and the right half of the reduced interval and go from there. If I have trimmed a sufficient amount, I advance to the next independent variable. So if I did a projection onto x for a two-variable problem, the next one is on y. If it's a three-variable problem, then you do z. When you get to the end, you loop back around to the beginning and keep doing this. And as long as you're getting 30% every time, you're making some kind of progress toward the solution. But the splitting step is key, because if you've got 100 solutions to this knot, the only way you're ever going to find all 100 of them is if there's some sort of splitting going on someplace. So this is what you do. And then, as you pointed out, Wolfgang, this is a slowly converging algorithm. You only get linear behavior. You get all of the usual problems with multiple roots, in that if you aren't very careful, you can miss things or count them twice. One of the things, I mean, I've been playing with this, and the test cases and the bug reports that come in from 200 million of these things every day for the last 25 years. So I'm certain I haven't seen it all, but I've seen a lot. You can get places where the root lies right on the midpoint of the interval where you split, and then you find the root twice, and you just have to account for all of these things, and it requires very careful coding to get this all right. This last bullet here, the accuracy can be improved considerably. You make a lot of problems go away simply by rescaling your independent variable to 0, 1 after every single reduction, and also scaling the spline coefficients so that the largest one in absolute value is either 1 or -1. The scaling of the spline coefficients doesn't change the location of the zeros. And when you take the pruned interval and reset it to 0, 1, you just have to keep track of that so that you can undo it as you wrap your way back out of all these recursive steps. But the scaling and the shifting really help a lot in terms of taking care of a lot of things that can go wrong. All right. All right, now here's Ito's intriguing idea that he published a few years ago. Look again at the graph of a univariate spline function and its zeros. And what we did in projected polyhedron was just to generate the convex hull of these control points and find the intersection with the x-axis. But Ito suggests something that both Tom Hogan and I found very intriguing, which is rather than do that, observe that a necessary condition for this to exist is that some convex combination of these control points has to give you the desired thing. That is, there's some value of x for which the function vanishes and for which the combination of the control points that you're taking, it's a convex combination. All the lambda I are greater than 0 and they sum to 1. And if then I attach objective functions, minimize x, maximize x, to that set of linear equality and inequality constraints, and solve those two linear programming problems, I'm going to get, he didn't actually explore this, a rather sharper bound. Ito discarded this idea at this point, saying no one would ever do this. You would be crazy to do this. Because solving these linear programming problems is at least 2 orders of magnitude more expensive, at least, typically, than just doing projected polyhedron. And so you'd have to, in order to do this, that has to be overcome. And then the other objection that he had to this particular method is, before I get to that, here's how the whole thing works for a 2x2 system. I have two tensor product spline functions, and I can write those things down. I have additional constraints. I have not only the constraints for F, but I have the constraints for G, and I have to find some value of X, some value of Y, such that the function vanishes and all the lambdas and all the mu's sum up to 1. And the lambdas and the mu's are all positive. And then I can solve those 4 linear programming problems over that set of constraints and reduce the size of the box. Okay, so again, it took him a paragraph to discard this idea, in part because solving these linear programming problems is so much more expensive than doing the projected polyhedron state. There isn't any reason to believe that linear convergence is really improved upon. And moreover, he was concerned about what happens as the number of dimensions of this system increases. As you go from 2 to 3 to 4, you're getting exponential growth in the number of problem variables that you have to solve, and this quickly gets out of control. But when we took a look at this, we said, okay, that's all true. I mean, what Ito says in that paper is all true. But where are these 200 million applications actually coming from? And as you start to look at the 200 million applications, here's a canonical one, the curve intersection problem. I've got some two-dimensional curve P, some other two-dimensional curve Q. These are curves in the plane. Where do they intersect? I have this separable problem structure. I can write my nonlinear equation as a sum of functions, nonlinear functions of smaller number of variables. So Ito rightly points out that if one were to do this completely in general, what you would get is a problem that has the number of spline variables equal to the number of spline coefficients in P times the number of spline coefficients in Q. But if you formulate this problem in a way that takes advantage of the structure that you started with, it's not M times N, it's M plus N. You don't get this exponential explosion in number of spline coefficients. And if this structure this separability structure occurs often enough, maybe you can take advantage of this. So here's the idea. All right. I think this even works on problems for which you have partial separability. I can't write this as 3 separate nonlinear functions of u, v, and w, but I've got one function that is a function of u and v, and one that's a function of v and w, and I don't get m times n times k. It's just m times n plus n times k, which is better. I can reduce that to a set of constraints. Okay, so I decided I would code this up in Python to explore some possibilities here. And so I took, to be fair to Ito, I took Ito's own test cases right out of his paper in which he threw this out as a bad idea. And I said, all right. He had what he called in this paper the naive LP method. And the naive LP method, as you can see, he's coded this up in complete generality. And you see that by the time, this is just an intersection of a number of hypercylinders in n variables. So in 2 variables, it's the intersection of a pair of lines. And in 3 variables, you get this. And in 4 variables, you get, I can't even begin to picture it. But what you know is that the number of solutions that you get to this problem is 2 to the n. And if you code this up using the linear programming method completely in general without taking advantage of the separability, you see that, as he said, the compute times are going to get out of control in a hurry. And so for the 6 variable problem, it's taking him over 2 minutes to solve that. When I did the 6 variable problem, taking advantage of the fact that this function, these f sub i's here, the xj's are all separate from one another. You don't have any cross terms in the whole thing. So if you take advantage of that in the B-spline expansion of those functions, what you're going to get is something where the number of problem variables is 3 times n and not 3 to the n. And when you do that, I had no trouble at all solving the 9 variable problem, finding all 512 solutions to the problem in a matter of just a few seconds. Because these are not large linear programming problems, and you don't need to solve very many of them. The other thing I observed when I ran this test case is that the size of the search tree is considerably less than what you get for projected polyhedron. And so that got me to thinking, okay, if at each step of the search tree of this algorithm, I have to do 100 times as much work, but the search tree itself has 1,000 times fewer nodes, maybe there's a big win here to be had. And so with that in mind, we ran some more tests. This is the one that really got to be intriguing. This is the same example as the previous one, except that instead of x squared, you've replaced everything with x cubed. That means that you only have a single solution to this system. And if you look at that number of LPs column right there, I can solve the 20 by 20 nonlinear system here, and I can find that root almost instantly. I only have there are only 80 variables in each of these linear programming problems. And I only have to solve 7 times to really isolate that root. Ito, for the 6 variable problem, when you don't take advantage of the special problem structure, he's up over 12 minutes on the 6 variable problem. And okay, looking better. This is another of his examples, the Broyden tridiagonal system. You can see that this is almost linear, except for that little xi squared term sitting in the middle there. And it has exactly 2 solutions. And again, not bad. I'm encouraged by this. Well, but then, of course, he had his 4th test problem in here. And this guy, there's no hope, because you can't take advantage of any of the separability. And I was able, he did not even attempt this algorithm on this problem. I did, and while the number of linear programs stays nice and small, the number of problem variables gets completely out of control. By the time I get to this 7 variable problem, where I only have to solve the linear programming step 14 times, I have already 3 to the 7th. How many is that? I didn't even calculate it. It's quite a few. 3 to the 7th variables, and this is solving that 7 by 7 system, I think, was the better part of 10 minutes of computation, because you've got a lot of problem variables. All right, so it doesn't solve the problem in general, but again, the focus here is where do those applications that I'm interested in really come from? All right. This is the one particular test problem that has been a thorn in my side for 15 years or more. It is a particular three-surface intersection problem. So I've got three surfaces, and I want to know what point do those three surfaces have in common. It is a 6x6 nonlinear system of equations in the variables u, v, s, t, a, and b. But if I take a look at this, my first three equations are of the form f of uv minus g of st. And my second three equations are of the form g of st minus h of ab. In fact, I've got three more equations I could throw in there, f of uv minus h of ab. And what I really, in fact, ought to do is to make sure that I don't solve the one that has the two largest number of spline coefficients in it. Always throw that guy out and solve the other two. So take the one of those with the largest number and pair it with the one with the smallest number, and then the guys with the two smallest to reduce the complexity. Well, projected polyhedron takes over 35,000 subdivision steps to find the, I think there are 4 solutions to this system. 35,000 subdivision steps. And yet when I try this using the linear programming based method, I can find them in 13 subdivision steps. There's this huge payoff. And so here it is. I really have the case. This is an example of the case where I have a 3 order of magnitude reduction in the size of the tree that I have to search in order to find the solutions, but only about a 2 order of magnitude increase in the computational cost of each of the nodes. I get an order of magnitude improvement in the runtime for this just by focusing on this particular algorithm. Okay, so naive LP is what Ito called this particular method. What do I really need for this to be a go? I've got the Python implementation. We had to decide, are we going to go for this? Should we try to create a production version of this? What's going to happen if we do it? What are we going to need? Well, we're going to need, as I said, these much smaller subdivision trees than the ones we got. A fast linear programming solver, preferably one that can take advantage of the sparse linear algebra that you're dealing with. A hot start capability. This is, again, if you're particularly if you're going to be using a simplex method-based solver, because what happens in that case is if I'm solving an n by n nonlinear system, I have 2n linear programming problems that I have to solve, but all 2n of them have the same feasible set. So I only need to do phase 1 of the simplex method, find a feasible point once, and then phase 2, the optimization step, I can solve that 2n times, taking advantage of this hot start capability where I have already pre-computed the feasible set. The other thing that I'm really going to need here is most of the applications to be separable in some way, so I don't get hung up on this thing that Ito was so very afraid of when he published his paper. So I went through and looked through the applications. There are some non-separable problems, and in every case that I could find, those are 2x2 nonlinear systems or 3x3 nonlinear systems. You don't have the 5x5 or 6x6 nonlinear systems that arise without some form of separability. So all of these problems, including all the ones that were on the first chart that I showed back at the beginning, you've got some sort of separability here to keep the size of these linear programming problems down. Now the last application is one I haven't talked about yet, which is the composition of spline systems. So what if I've got nonlinear equations that are of the form f composed with g equals 0? and F and G are both tensor product splines. Those are certainly piecewise polynomial functions, but if you are diligent about trying to figure out where one polynomial piece blends into the next, you're going to find curved knot lines all over the place, and it's a mess. You don't want to take you don't want to solve something like that by looking at what's going on with the polynomials. Well, one thing that you can do in that particular case, did you have a question? This is the, yeah, exactly. You may have a more proper name for this than, I call it the Betts trade-off. The basic idea here, and John Betts was a technical fellow at Boeing and a colleague of mine who solved optimal control problems. I mean, he put satellites in orbit by optimizing trajectories, and what the trade that he was always willing to make in these nonlinear optimization problems that he wanted to solve is to increase the problem size a little bit if you're willing, by trading away some nonlinearity. And that's in effect what you're doing right here. If I have F and then some inner map of this composition given by U and V, so this is a case where I've got a curve that lies on a surface intersected with another surface. And so the curve is properly given as in the parameter space of the first surface. The image of that curve lives in the parameter space. If you compose the surface map with that, you will get as a function of t the exact curve that lies on that surface. Well, you can reformulate the problem as a tensor product spline system of this form. And again, the thing is magnificently separable. And in fact, even in those last two equations, U hat and V hat appear, they're linear. It's wonderful. So that's how this can be done. This works, the linear programming-based approach for things like this work. I have not yet worked up the nerve in the aero community at Boeing. Some of the Boeing commercial airplanes aero guys create models in which they have F1 composed with F2 composed with F9. The biggest one I've ever seen is 9 spline functions composed with one another. Now, a big chunk of that is bad practice on their part because some of those compositions are merely trims or linear reparameterizations or something that can be handled much better in a different, they aren't truly additional nonlinearity. But when I try a few of these kinds of things using this linear, it's fantastic. Is there a better name for this than the Betts trade-off? This little trick? It's a lovely trick.
Yeah, it comes in many variants. It's used in PDEs as well.
Yeah.
Sometimes. It's a nice.
Yeah, it really is. 5 by 5 really isn't so much worse than 3 by 3. And if you're dealing with things that turn out to be degree 3 polynomial systems rather than degree 6, you're better off. Okay, so the composition of functions, here are some of the BCA, the Boeing Commercial Airplanes applications. Structured meshing, again, you're constructing a mesh map so that the isoparms form a nice mesh. Deformable, there's a lot of, aeroelasticity is a big thing. And have any of you flown on the Dreamliner or the 787? Yeah, okay. Well, if you looked out the window, you will have seen from the relative position of your seat that the deformation of the location of the wingtip moved almost 4 meters up relative to where you were sitting when the plane was in flight. There is tremendous deformation of the structure. And the deformation of the structure is what is taking up all of the load. It is what keeping the airplane in the air. So one of the ways that this gets modeled is if I have a surface model of an airplane wing. Again, it would be a Tensor Products spline mapping from R2 to R3. I can construct a deformation map that by taking the output of the structural analysis that has the deformations, I can construct another Tensor Products spline map from R3 to R3 that tells me where each x, y, z location in space moves to, x hat, y hat, z hat, under this structural deformation. And if I then compose that map with my airplane model, it's going to give me this kind of a deformation. And I'm going to be able to track the structure. There are many, many issues in terms of constructing those kinds of spline maps all on their own, but there are lots of applications of this idea. Okay, some additional thoughts, and I will wrap up here in a minute or two. Over on the left, I have the search tree for projected polyhedron. Lots and lots of nodes, very little computation at each one. But what I find over here in this LP-based method is I have a much smaller search tree with these big, beefy nodes. 100 times as much computation happening at each of these things. Well, all of a sudden now this becomes much more amenable to doing this in parallel. Over here, I don't want to fork off 30,000 separate threads and have all these thread race conditions. And trying to do something like this with little tiny bits of computation in parallel, it doesn't pay off. But with big, beefy nodes where there's lots of work to be done at each node, now you can get this to pay off because the amount of work overwhelms the overhead in terms of creating the separate threads. So you've got a method that, from a parallel computing point of view, looks better. All right. Well, we talked about this already. If you do this with the simplex method, there are 2 phases. The first phase, you find feasible points. Then in the second phase, you solve all 2n linear programming problems. Those can be done in parallel because they're all independent of one another. So on one node or one thread, you perform phase 1, find the feasible point. Then you create 2n separate processes and find all of the mins and max in parallel. But potentially an even better thing to do is to scrap the simplex, and I have not tried this, is to scrap the simplex method altogether and try to go after this with an interior point method. If you look at the details of the interior point algorithm, what you see is the only place where the linear functional, which is the objective function, appears in the entire algorithm is in one step where you are solving a linear system of equations. It appears as that vector, which is the linear functional, appears as the right-hand side. Well, you can just perform this linear system solve with 2n right-hand sides and do this all simultaneously. That's not the major expense of the algorithm. So the fact that you're doing 2n of these things is not much more expensive with an interior point method than if you're just solving one. So there's something to explore here. Okay. This naive linear programming method that Ido Hanil wrote about and then discarded 2 paragraphs later, I think it's a way better method than he thinks it is. And at some point when I run into him at a meeting, we're going to go out for dinner and we're going to talk about this. Because he has what I think is just a brilliant idea here. And he's selling himself far too short to not take some of what this method has to offer more seriously. Right. I think I will stop there. Thank you.
Are there any questions? Yes.
It just occurred to me when you talk. On these cases where you have the non-separable problems, they are of smaller size, right?
They tend to be. But the composition of functions thing, this is where you're getting these 9 by 9 systems out.
But for the non-separable cases, would it make sense to go to find the zeros of the control polygons, say in the Bézier representation? Because then you are looking for zeros of affine functions, and then we find around those. We represent the final term in that neighborhood and constitute this. Had that been tried?
Not that I'm aware of. You're suggesting a much sparser representation of the function in the early phases. Yeah, that might work. There's one other thing, particularly for this crowd, I wanted to point out. Yeah, let's take a look at this. Projected polyhedron as a method depends crucially on the tensor product structure because you are projecting everything onto one variable. This method doesn't depend on that tensor product structure at all. So in particular, if the BI and the CJ are any old functions which form a partition of unity, this method works unmodified. So this would work for box splines. This would work for... There are simple modifications to this that will work for far more general things. Imagine that the BI and the CJ are all positive functions which are bounded. You can modify the constraints appropriately, and this method will still work for finding zeros of functions in that generality. So I think there's maybe a lot more here than meets the eye.
Any other questions?
How
Yeah.
about the robustness, since that was one of the criteria why the picture
Yeah. That's a scary question because I have the 25 years of experience of knowing how to do all of the adjustments that needed to be made with projected polyhedron. And I don't know any of those adjustments that need to be made to make this work. But what I can tell you is I have a list of all 178 of the really hard problems I've seen over the last 25 years. And so I'm not starting at the same place I was 25. I know what constitutes a hard problem, and I've got lots of examples of them. And so it's a question of doing a lot of work while immersed in the code and getting this to work. The other thing I've got going on, most of the work over the last 25 years has been done by me, but I've got this brilliant young hotshot who is working on implementations of this with me, who does just exquisite work, and I like, so he and I are going to have some interesting discussion. He's just at the point, we did decide to go ahead with this and put together a full-scale, serious industrial implementation of this method, simply because our test results had been so promising. And he's at the point where he's just about ready now to say, okay, I've solved the 12 test problems that you gave me. Do you have something harder? And ask me again in a few months. In fact, you know him. This is Craig Bosma who's doing this work. He spent a week with you, so you know him quite well.
Any other comments or questions?
May I ask a naive question? What happens to the airplane when it takes off? When the pilot is pulling the handle, what are changes happening to aircraft, which possibly?
Well, there are the big structural changes. And structurally what goes on is when the airplane is on the ground, the engines and the wing are being supported by the fuselage, right? So if you can imagine, the wings are drooping a little bit because all of the weight is on these wings. The minute the airplane leaves the ground, the situation is completely the opposite of what it was.
I understand, but it's running. It's running on the lane, yeah.
Yeah.
What happens? Why is he pulling the nose up and getting into the air? What happens?
What happens? It happens V0. It is a velocity that has to be calculated for every single flight that you're on. And how that calculation is done would be in and of itself a wonderful talk sometime, because there are all of these spline models of various things, and you have to calculate this speed. But what happens in particular, once this speed is calculated, and it is calculated to be the right speed, the plane rotates, and the point of attachment of the flow on the leading edge of the wing now, instead of being here, is now at this much lower spot on the wing. And so what you have just done is to increase dramatically the length of the streamline on the upper surface of the wing. Do you have a piece of paper? No, I need a piece of paper. It has to be a piece of paper. So what happens, of course, it's Bernoulli's effect, right? You've just
Not the question about physics. I mean, the airplane is running. Yeah. So what happens? The shape of the wings. Because I watched the wings. Wings are the same. Yeah. What?
No, at a certain speed, the lift is big enough.
Yeah, I know. But
and the balance in the airplane allows the nose to be up earlier than the tail.
Oh, okay. Yeah. It's the wiping surface. It's the wiping surface on the airplane. That's the question that you're asking. How do you achieve rotation? Is that the question? How do you rotate the plane? This will work. You see the horizontal stabilizer right here. That entire thing, it is tilted down to create a big downward force on the tail. And so it isn't so much driving lifting the nose as it is driving the tail down to force the nose up, because it's the teeter-totter effect. Now, there are some military configurations where you don't have enough tail force to be able to cause the plane to rotate. And they've done all kinds of goofy things with pogo stick nose wheel landing gears, where you want to rotate the plane, you just extend the landing gear on the nose to bring the nose up. But there is something that you are absolutely right. You have to do something to cause that nose to pop up off to create the high lift condition. Yeah, it's
way more than 5 for this big 380.
The A380 might have a 5-meter deflection. Yeah, it's a lot. Next time you're in a window seat of an airplane, take a look. You'll notice it. Yeah, and it's really magnificent that the structure. There are any number of. For aluminum wings, the problem is not so severe for composites, but for aluminum wings, there are all kinds of really interesting manufacturing treatments that are applied to, because it's an aluminum wing, and you're doing this to it every time well, you can imagine if you take the the pop top of a beer can, it's not going to survive 60,000 of those cycles. If you're lucky, it will survive 2. And maybe on the 3rd or 4th one, the tab comes off. Well, so what on an aluminum wing airplane, what is done is to shot peen the aluminum. That is to bombard the aluminum skin with all kinds of lead shot hundreds of thousands of times to create all of these little tiny dents in the wing. So that what effectively happens in that case is that no matter how you flex the wing skin itself stays in a compressive state. You never have the tensile state. And so you don't have these alternating states of compression and tension that lead to the metal fatigue. So there are lots of clever things that are done to make this all work.
Well, this is really a very fascinating talk. So next time when you go up the plane, let's remember spline functions. Okay, let us thank Thomas for a wonderful talk.